Okay, so let's do some example of this transition function. So here, for example, from S on epsilon, well, this is just going to be the epsilon reach of S. So we already computed it. This was S, D, and A, right? Okay. Okay. What about on 0? Well, we already know that we can be in S, D, and A. On 0, of course, from S, we can stay in S. So this is going to be S. If we are in D, we are going to, we cannot do anything with 0, so it doesn't matter. And from A, we can go to B. So this is going to be SB. And now, and of course, we need to do the epsilon reach of that. So let me put in double quote because we really need to do the epsilon reach of that. So this is going to be SDBA, right? This is the set of states that the automata might be on after the input 0. Okay. Next one. Delta star of C0, so we're in C. Okay, so first we need to do the right, we need to do the epsilon closure. So epsilon reach of C is what? Let's see. It's C, of course, it's D, it's G, and it's A, right? This is the epsilon. Okay, so on 0, we can do a lot of things, right? So C itself on 0 doesn't do anything, right? D, on the other hand, when it gets 0, also cannot do anything. G, if we get 0, can stay where it is, so G is one of the options. And if you're in N, you get 0, you can get to B. Okay, so which is, a bit counterintuitive, but it is what it is. Okay, and finally, delta star of B, 0, 0. Okay. Well, so now we need to do all this. Okay, so with a 0, we can, so this is delta star. Let's first compute delta star of B0, okay? That will make things easier. So B0, we can go to, we can of course go to, well, we cannot stay in B, so B is not true. We can go to C, and it's epsilon closure, which is GDA, right? G, D, and A, right? Okay. Now that we apply A to it, let's see what we can get. So, okay, C, when you apply 0 to, well, let me put it in double quote because we might have to apply epsilon transition. Okay, C, if we get 0, we cannot do anything. G, we can stay in G, right? G, we can stay in G. D, if we get a 0, we don't do anything. A, if we get a 0, we go to B. So this is G and B. So this is G and B, but for G and B, unfortunately, they don't have any epsilon transition, so this is really just G and B. Okay. So that's this the transition function here. And as you can see, this is becoming quite tedious to do manually, but it is what it is. Okay. So now here's another definition of execution of an automata. So we are going to write that for an NFA n, Q can reach P on a string W. We write it with this bizarre arrow notation. We will write this if, we start at the state Q, and now there is a sequence of states, right? The sequence of states is, in the beginning, it's equal to Q. The first state in the sequence is Q. The last character in the sequence is P. And the important thing is that we can break the string W. The string W is just a concatenation of those k characters, right? So W is equal to x1, x2 to xk. Importantly, those xi might be epsilon, right? So the string W might be in fact shorter than k, but it, in the maximum it can be of length k. And now the I plus one state is a state you can reach to from the ith state using a character xi plus one, which might be epsilon or a real character, right? So if you draw it, this is just saying that you have the state P. You can do epsilon transition to some other state. Well, in fact, since we are now including epsilon, maybe it's easier to think about epsilon. So we have a set epsilon. We do epsilon transition to some state. We take the first real character, let's call it W1. You do some epsilon transition. You get to another state. This epsilon transition might be, of course, several epsilon transition edges. You take the second character, W2. Again, you do epsilon transitions, and so on, right? You alternate until you handle the last character in W. You go to a state, you do epsilon transition, right? And you get to the state. Oops, I said P, and of course I should have written Q. And you reach the state P, right? And if you have this sequence, then this sequence is essentially you reached from Q to P, and you use the string W to do so, right? So if you can do that, then this notation says you can reach P from Q using this string to travel. And now we can define a transition function from QW to just be all the states that you can travel to from Q using the string W. So this is another definition, and it's a bit cleaner once you get used to this somewhat bizarre way of thinking about things. Okay, why non-determinism? So non-determinism turns out to be very important in theoretical computer science. We will encounter it again in the end of the course when we speak about NP completeness and NP hardness. The way to think about it, it makes the computation model stronger. Now, for automatas, finite automatas, it doesn't really change the power of computation, but it does give us an expressive power, which for our purposes would be very important because, as we will see, the NFAs are really equivalent to DFAs. We will see that. And on the other hand, it's very easy to show that NFAs and regular expressions are equivalent, and that would give us what we want as far as showing that those three representations are equivalent for regular languages. And this is it.